Okay, in this part of the presentation we're going to look at network security. Another associated presentation will look in more detail at the configuration of firewalls. It's the aim of this presentation to give some general background into network security and some of the key components that are involved with it. So we'll look at firewalls, screening firewalls, and also stateful firewalls, NAT, Network Address Translation, a quick introduction to the PIX ASA firewall, a look at proxies, VPNs, and on to tunneling. Okay, the major problem that we have from a security point of view is that we tend to take a layered approach where we might have a network infrastructure, some application protocol, and then the applications and services themselves. The major problem that we have is how to keep the whole communications secure, especially as we tend to look at things in a layered approach. So in this case we might have firewalls and proxies at a network infrastructure. We might have some application protocols such as HTTP, TCP, IP and so on. And we obviously have our applications which sit on top of these application protocols, and increasingly we have our services. A major problem tends to be the interfaces between each of these layers, in that each layer themselves can be relatively secure, but the glue which binds these layers together can be relatively insecure. So we need to make sure that we have an integrated approach and understand each of the elements, as a weakness in one area can compromise the whole system. So the two founding principles are CIA, confidentiality, integrity and insurance, and AAA, which is authentication, authorization and accounting. An example communications channel between Bob and Alice might look something like this. We have a public channel, the internet, which cannot be trusted. We might have some firewall on the gateway of our network, and it's up to this firewall to filter ingoing and outgoing traffic into the organization. We might have some router, intrusion detection systems, and we typically connect to a switch. On the other side here we can see similar type of architecture, and in this case we might have our servers for our organization. A typical design is to move our servers, our forward-facing servers, the servers which can be accessed from the outside, into a demilitarized zone. And for this we might set the firewall up as the first protocol to stream off traffic immediately into this demilitarized zone, and for it to stop any incoming connections from outside into our trusted network. So forward-facing servers typically go into a demilitarized zone. Some of the symbols that we'll see for firewalls, switches and routers are this one, which is a router running some firewall software, in this case a Cisco firewall. We have a PIX ASA, as we'll see, which is a stateful firewall, and a PIX firewall and an ASA firewall, which is the new range of firewalls from Cisco. We'll also see network address translation devices, intrusion detection systems, and Cisco switches. We can protect a network in many different ways at many different layers. At the most basic layer, layer 2, at an Ethernet layer, we can segment our network up into VLANs or virtual LANs. In this case, these two nodes connect to each other and are basically on the same network, and these two machines are on another network. Without any routing software, they cannot communicate with each other because they are separated logically into VLANs. It is up to a higher level device such as a router to allow them to intercommunicate, by which time the router can decide which communication is allowed between the VLANs. At the next level we have a typical screening firewall. In this case we filter for IP network address filtering, and also at the TCP or transport layer. And with this we filter for source and destination IP addresses, and we also filter for source and destination TCP ports. For example, a web server runs off port 80, and the firewall would check the destination port. If the service wasn't allowed, then it could stop the port at the firewall. In this case, we would allow the firewall to have a destination port of 80 for this machine, a destination port of 21 for the FTP server, and so on. Then we can have stateful firewalls, and stateful firewalls can deeply inspect any data packets, and they can filter for the network layer, layer 3, the transport layer, and also can examine the application protocol to see if there are any problems with it. The other thing with a stateful firewall is it keeps track of a connection. In a stateless firewall, every packet is new to the firewall and it does not trace back. In a stateful firewall, the firewall keeps a track of where the connection is and makes sure that things are done in the right order. And then at the top we can have an application filtering system, and as we'll see we can use a proxy server in this case. With proxy we'll check users typically and all the details of the application. These are typically known as application gateways. Screening firewalls are one of the most basic techniques involved in security and can be seen as a frontline defense. They can be easily breached, but they are a useful method of first-line filtering. The basic firewalls that we have are either a software firewall, and with this we typically purchase a standard server, such as one that runs Windows, VMware or Linux, and then we purchase firewall software which actually runs on this hardware. This type of hardware tends not to be optimized in the same way a hardware firewall is. Checkpoint is a good example of this type of software. We can also get a host-based one, and for this, Zone Alarms, which is also owned by Checkpoint, is a good example of a host-based firewall which runs on client hosts. We can have a Linux firewall, software firewall, and also we can get Checkpoint firewalls which have dedicated hardware, such as the Nokia firewall. Another type of firewall is a hardware firewall, and with this we have a dedicated device which has been optimized for running routing software and also firewalls. We can have a non-stateful firewall, and that's with a router with firewall added to it, and that does a packet inspection. Each packet is inspected one by one, typically for its source and destination address, or for its TCP source and destination port. We can also have a stateful firewall, such as the PIX and the PIX ASA. For software firewalls, they're typically fairly easy to configure, but tend to be slower in their filtering because the hardware itself has not been optimized. For example, running on Windows NT or Windows 2000 will not be optimized in the same way that a Cisco firewall will. They tend to be less expensive because we are buying software and a license for software rather than hardware, and they can also be used on a range of computers and operating systems. For hardware firewalls, we typically have an optimized engine architecture. They tend to cope better with traffic flows, in that a software firewall will typically have a jump in its, will have a reduction in its performance whenever we start to apply firewall rules, where a hardware firewall will typically cope more gracefully with these. And the hardware device will typically have improved failover so that they can cope much more gracefully with any problems. So basically with our filtering, we typically filter either with a source and destination IP address or a source and destination TCP port. We can also filter for the protocol type too. So if we look at the basic header for our IP packet, and also we look at the header for the TCP part, we can actually see the details. In this case, for the IP header, these first 4 bits are important because they define the version, IP4 or IP6 typically. We have things such as the time to live field. Time to live field is a method that is used to stop a packet from transversing the internet forever. Each router that it passes over will decrement the time to live field by some amount. When it becomes 0, then the packet is deleted. Protocol field defines what comes next. In this case, it's TCP, but it could be any other. It could be many other protocols, and one of the great successes of IP is that it can actually carry many different types of protocols, including voice over IP or routing tables. The 2 key areas are the source IP address, 32 bits here, and the destination IP address. The source address is where it came from, and the destination address is where it's going to. In the TCP part, we have a 16-bit field, so our numbers go from 0 to 65,000 and odd. We have a TCP source port and we have a TCP destination port. In a client-server architecture, the server has a standard port that we connect to and is well known. Even in peer-to-peer communications, we still have this client-server architecture. So for example, we have port 80 here. So the client picks a port that it's not using, say 1024, and that becomes its source TCP port. It connects to a server port. So when the packet is traveling in this direction, it will have a source port of 1024 and a destination port of 80. Once it's traveling back, it has a source port of 80 and a destination port of 1024. There are a few other things in the TCP header. One of the most important is the flags area. Typical details. We can see here this is the Ethernet source and destination physical addresses, MAC addresses are here and here. Then we have the source IP address, destination IP address, source port, and the destination port. Then at the TCP level we have the flags, sequence numbers, and so on. So the details we typically see relate to the parameters that we see within inside the headers. A typical firewall that's used is a Cisco firewall, and with this we have what are called access control lists. Access control lists will be covered in more detail in an associated presentation. This lecture is just intended to show some basic details. So in this case, what we want to do is that we want to block a certain network from contacting a certain destination. So what we do is that we define an access control list, and this access control list is applied to an interface here. In this case, we're applying it to the E0 interface, which is here. So the firewall checks on this port either for incoming traffic or outgoing traffic. So we can apply two directions on each interface for a Cisco firewall. In this case, we're going to be checking the incoming traffic. So in this one, we assign an IP address to the interface of 156.1.1.130, and we filter for this access list. So basically, if we fail to match any of the access lists, then it will drop the packet. Each of the access lists is actually checked one by one. So in this case, the access list says deny anything from the 156.1.1.0, and then we define a subnet mask or a wildcard mask to define which parts of the address we need to match. Whenever there is a 0, it means we match this part completely. Whenever there is a binary 1, in this case 255 is 8 ones, so it means all of this part. It means that we ignore that part. So in this case, when we're checking the addresses of the data packets coming in, then anything with 156.1.1 will match this statement. As we have applied a deny, then that data packet will be dropped. So data packets coming from here will be allowed to go through, and from here, but any data packet from here will be dropped, because the source port is one of these addresses. These are defined as standard ACLs. Unfortunately, what we can see, if we're trying to block Eve from this network, then by applying it here would stop Eve getting access to this network over here. So if we only want to bar Eve from this network here, we would apply as near to the destination as possible. In this case, we would apply the access list on this firewall. So we can see here that if we applied it here, then the access to this network would be blocked. We can also define what's called an extended ACL. An extended ACL will check both the source and the destination IP addresses. So in this case, we deny a certain host access to a certain network, and we permit everything else. So anything with 156, anything from this host will be barred from getting access to this network. And then in this one, we can say the same again. We can take a whole network. Anything coming from all of this network to that same network will also be barred, and we allowed everything else. So data packets coming from here will be allowed. Data packets going to any other network rather than the 70.1.2.0 network will be allowed, but anything going to that network from these hosts will be barred. So the good thing about an extended ACL is much more targeted. So now what we can do is that we can actually apply it to an interface early on, and we can filter it. So we can also filter for port numbers for TCP and UDP. In this case, we're filtering when for a certain network for a given protocol. The two basic firewalls that we tend to have are an open firewall and a closed firewall. In an open firewall, we typically deny, and then we permit. So that allows virtually everything to go through, but we deny certain services. In a closed firewall, we typically have a closed, deny all, and then we say permit, and so on. Network address translation, or NAT, is one of the key principles that are involved in security, and it helps us to isolate an internal network from outside. Basically, what the NAT device can actually do is that we can have a single or a limited number of external addresses that we use. So these are IP addresses which have got a viewpoint on the internet. And then inside our own network, we can have our own private addressing scheme. Then the NAT device takes the source address and the source TCP port, a destination IP address and a destination port, and then remembers it and then remaps it to an external address. So in this case, the 192 address has been remapped to a public facing address, but now the TCP port source port has been changed. The destination port stays the same, and the destination address. So in this case, the NAT device has translated the IP address to a public address, changed the port, goes to the web server, and the web server could take a note of that address, but we've actually hidden the original sender of the address because it's not known what that original address actually was. So then the web server sends back, and it sends a destination port of the address that it received it from, and also that port. Then when the NAT device picks it up, it remembers the original translation and translates it back into the original address and the original port. In this way, we isolate from outside. This is a private address space, and this is a public one. So it hides the network. It also bars any direct contact with a host in our network. It increases the address space. We might only have one address, one IP address outside, but now we can have multiple addresses inside, which are all translated. This typically happens on a home network, where the ISP allocates one IP address for the connection, but there can be multiple devices in the home network which are translated through a wireless access point, typically through NAT, into this public space. And it allows us to create our subnetworks easily. So with inside a NAT device, it basically creates a little table. So we have what the connection was inside, we have what it's translated to on the outside, and where it's actually going. When the data comes back from that destination address and destination port with these details, then it retranslates the details back into something that means sense on the inside network. When new connections are created, basically it will pick another port, and as long as it doesn't run out of these TCP ports, it can keep a track of each one. So we can see here we have 3 connections to the same web server, but each time it changes the port into a unique one, so that when it comes back from the server, it will be able to retranslate it back into the correct address and port. This is a new connection here to another device. The most basic form of NAT is to actually do a static translation. and we'll see this is the least secure, where we have one address on one side and that maps to a direct IP address on the outside. So with this type, it is possible to make a connection back into the network, because the translation is a one-to-one translation. It is good though for traceability, in that anything that's logged on this address here can actually be traced back to this address, but it doesn't hide the actual originating node. The method that we've just seen is called IP masquerading or dynamic translation. In this case, we take multiple IP addresses and we map them into in this case just one address. And the table itself is dynamic. Whenever a connection is broken, then we can recreate that mapping again. With this mapping, we can also have load sharing. So we might have a server farm behind NAT, and the NAT device keeps a track of how loaded each of the servers are. So when a new connection comes in for a server, then the NAT device can send it to the actual device which is least loaded. In this way we can load share. If a server goes down, the NAT device could also detect this and make sure that a translation was not made to that server farm. So with NAT we kept isolated, so it's possible for us to create a connection with the outside, but it's not possible, apart from using static NAT, for a connection to be initiated from outside into a host. So for example, if this was a home wireless network, it's not possible for somebody to directly connect into a device. Unfortunately, there are some protocols which require a server port to be set up on the machine and for a connection to be made. Examples of this include FTP and IRC, where when the connection is initially made for FTP, the server must create a server port, which means that the external device must be able to trace back into the host which initiated it. This is known as backtracking. The NAT device remembers the connection and makes sure that a connection can then be made back into the device. Unfortunately, we have a problem with static NAT. Obviously, there's a one-to-one connection and it could be possible to connect back in. Dynamic NAT is better, but once the connection has been made, then it might be possible for an intruder to backtrack into the device. So in this case, Eve has allowed a connection onto her server. Once the connection is made, there is a backtracking possibility into the device. Eve could also get access to the NAT table, and so that any connection that's made would not be sent to a destination but could be sent to Eve's site. The problem with screening firewalls is that they examine each packet one at a time. So if the packets were out of sequence, it won't be able to detect that, and it cannot remember in which data connection is in. So stateful firewalls allow for a much more deeper understanding of the actual state of a connection. And the key identifying trace is defined at the start of a client-server communication. Virtually every communication that happens on the internet involves client-server communications. So we typically define a server, and a server is really just a device who is listening on a certain TCP port, and a client is the device which connects to it. Any computer, any node can be a client or a server, but a server will typically sit and wait on a certain port for a certain service. The first thing that we see is a small TCP packet that is sent out with the SYN flag set. So that is sent out to the server saying that the client wants to connect to the server. So in this case, the SYN is sent from the client and then the SYN is received by the server. The next thing that is sent is the SYN acknowledge. If the server wants to accept the connection, it sends back a SYN acknowledge flags in the TCP header back to the client. There's some negotiation that goes on, but basically if the client accepts that connection, then it sends back an acknowledge. The acknowledge goes back and the connection is now made. The key thing is that they will have negotiated the ports that they're going to use. So on the server side, it might be port 80, and on the client side, it might be port 1024. For the time of the connection, the IP address of the source and the destination and the TCP ports that are used are completely unique. No other connection in the whole of the internet will have those details. So it is these three flags that we detect to determine the start of a connection. We can see here an example. There is a standard DNS trace here where we're asking for the name of a server, and the DNS server responds back with the IP address. The client then sends a SYN flag to the server. In this case, the client has selected port 2013 with a destination port of 80. So the SYN is sent out, source and destination ports, source and destination addresses. If the server is willing to receive it, it sends back from its port 80 to port 2013 a SYN acknowledge. You can see the SYN acknowledge here. It's coming from port 80, going back to port 2013, source going to the destination. Once the client is happy with this, then it sends back on its port an acknowledge. Here is one of the flags, and that's from our client to our destination. There are a few other things which are negotiated, such as a sequence number, an acknowledgement number, and so on. A good example of a stateful firewall is the CiscoPIX or ASA firewall, and these are one of the most widely used firewalls. Basically, it can support firewall rules in the same way as normal Cisco devices can. We use the standard commands of access list and access group to block and permit traffic. It can also work at an application level so that we can actually filter for URLs. We might define certain URLs which are allowed and which are not. We can do port blocking, and we can also fix up certain protocols that are often difficult. As we've seen, FTP and IRC are two difficult protocols to deal with. The PIX ASA firewall understand how these protocols work and try to fix them up. We can have a cut-through proxy. We'll see proxies later in this presentation, but the good thing with proxies is that we can actually authenticate the user. Before the user is, say, allowed on to the internet, then we might ask them to authenticate themselves through some means, maybe a username, password, or biometrics, before they are allowed out of the system. We can do intrusion detection systems. We can detect threats to the network, and then we can act on these through some shunning. The PIX ASA also supports encryption, where we can set up VPN connections using tunneling protocols or IPSec. And it also supports failover. A firewall is typically a single point of failure. The last thing we want is for a power failure or a crash on a system. It might stop the whole network from working. So the PIX firewall typically has failover detection where another device can sit and monitor the main device. If it detects that it's crashed or isn't working correctly, then it can take over. Typical PIX devices that we have are the small scale PIX 501, fairly limited processor, small amounts of memory, small throughput, can handle up to about 7,500 connections. There's only one internal connection and one external, so it's typically used in a small office. For a remote office, we have the 506E, which can handle a 20 megabits per second throughput, 25,000 connections, and again it has two connections and an incoming connection and an outgoing connection. For a medium-sized office, we have the PIX 515. It has a fairly beefed up processor, fairly good throughput, it can handle quite a lot of connections. It's available in two license forms. It's one of the few devices which has a license. It's restricted, which does not integrate an accelerator for encryption. We can and it does not have failover support. And then there's an unrestricted license which does have failover. The throughput drastically reduces when we're using encryption, so we can see here that it drops from 188 down to 22. But if we use an accelerator, then it can be increased greatly. The 525 gives us increased number of connections. We can see 4 connections here. We might have in and out and 2 demilitarized zones, but there's also potential for other network connections in it, up to 8 in this case. Supports failover and has quite a large number of connections. Then we go into the 353. Fast processor, has quite a lot of memory that can be upgraded and can support 500,000 connections with failover and up to 10 connections, possibly in, out and 8 DMZs. The new range now includes the ASA 5520. It's a Pentium architecture, and it has integrated VPN, a fairly high throughput, and a massive amount of connections. Okay, with the firewalls, they've typically revolved around examining data packets for their source and destination IP addresses and also for their application layer protocols. Unfortunately, we haven't seen any user authentication, so it's often difficult to tie up actual users with the with actual activity. Proxies are one method of doing this. With an application proxy, what we have is that for Bob and Alice to communicate, we must go through a proxy. In this case, when Bob is communicating with Alice, he goes through the proxy server and onto Alice. So the communications are done through an intermediate source or a proxy server. And it's in this proxy server that we can examine deeply the application layer protocol, and we can also make sure that Bob and possibly Alice are properly authenticated, and we can even filter it at this level. These are typically known as application gateways. So the advantages of them are that we can have a user orientated authentication. So in this case, Bob might not be allowed to communicate unless he's properly authenticated onto the system. We can have user authenticated login, so we could actually log Bob's activities because we've already authenticated them. And we can also have user orientated accounting, where we might measure the amount of time a connection took, the amount of bandwidth, and so on. The disadvantage though is that we typically need a a proxy for each of the different protocols that we're using. So we might need one for FTP, another one for Telnet, and email, and so on. But now, through the SOCKS protocol, we can have a one-box proxy. It is obviously slower because our communications, rather than going directly, are now going via the proxy. So if there are many connections, then the proxy itself can actually slow down. Along with this, it becomes a single point of failure. If the proxy was to fail, then it might be that there are no external communications. So it's a careful balance between this user focus, much more checking and accounting, against these problems. So one method that we might use is that we set up the firewall so that the only device which is allowed to communicate is the proxy. The only device which is allowed to communicate with outside is the proxy. So Bob tries to communicate directly with an external address, and it should be blocked by the firewall. And only if he communicates with the proxy will the communications be allowed out. There's also no direct communications with Bob in this case unless it goes via the proxy. So in this case, we say that we permit a single address, which is this address here on the firewall, and we deny everything else. And the same again for incoming. The only address which is allowed in is this address. So once we apply it, the only device which is allowed to communicate outside is the proxy. The only device which is allowed to receive is also the proxy. So any direct communications will be barred, either outgoing or incoming. We can improve this even further by having a dual homed system. We have a firewall on either side. Communications is only allowed through this firewall if it goes to the proxy, and again communications back only comes from the proxy, and the same on the other side. Only communications are allowed through the proxy if they come from through the firewall if they come from the proxy, and vice versa. This is a highly secure system. Bob must authenticate himself to the proxy to allow the communications out. So on the client itself, we set up our proxy, our proxy settings, and we run our proxy. So a very simple one here. It's doing a proxy for HTTP, FTP, SMTP, which is email, sending email, and then POP3 is receiving, and we bind it to a certain address. So the proxy will run there. And now what we do on the client is that we make sure that HTTP for web access goes to the proxy and is sent to a certain port, in this case 6588. So any web traffic that goes out is sent to that proxy on that port. The proxy then detects this and resends it out with its own address on port 80. When it comes back, it will then be changed back to be sent back to the client. So we've got FTP will go out on port 21 and so on. So typical protocols that we might use for HTTP is 6588. We have POP3, 110, SMTP 25, and so on. So we can see here we can actually focus on certain protocols where we can actually define a range of protocols that are permitted and bar all other traffic. So in this case, the only protocols that are allowed out are Telnet, FTP, HTTP, and POP3, and only from this host. So one of the advantages of running a proxy is that we can actually have accounting or logging, and we can see here that the proxy itself has logged all the connections. for the source and destination and the time. So the proxy allows the host to be hidden, so the IP addresses of the actual sender will not be seen on a destination. So the logs on a destination server in this case would only contain one address, even though there might be multiple addresses originally. We can use private addresses. They don't have to be public facing, only this address has to be public. We can log data packets. We can do some user authentication, and we can isolate our nodes so they can't be connected to from outside. Only communication with a proxy is allowed. Another key area in security is the usage of VPNs, and these are becoming even more important as we move towards remote working and mobile connections. With VPNs, and what we might have is that Alice and Bob might be communicating, and the problems are that Eve could eavesdrop on a public network, and also Eve could change the data packets as they traversed over the untrusted part. Also, Eve could set up an alternative gateway, so rather than going to, say, a corporate network, then the data could be streamed off onto another gateway. So what is really required is encryption to keep things secure, authentication to overcome the spoofing problem, and also we need to authenticate the data packets for integrity to stop Eve from changing them. So the typical methods that we use are point-to-point tunneling. In this case, we tunnel from one place to another, we encrypt the data, and we tunnel through the network so that no one can actually interpret the data that is sent. Layer 2 tunneling protocol is another one. The downside of this is that this tends to be a proprietary protocol. One of the best methods is IPSec, which is an open standard for both encryption and authentication. And more users are now connecting to remote connections using IPSec connections for their VPN network. Basically what we can have is that we can have a tunneling mode over a trusted network where that takes an unencrypted traffic and then tunnels it through the public network and then decrypts it again on the other side. The other method is to have end-to-end, where we have one host and another. They communicate, and the whole of the communication transmission is encrypted. The disadvantage with this method is if this was a corporate network here, then we could have intrusion detection systems and scanners and so on, and they will not be able to detect any threats because all the traffic is encrypted. So typically from a corporate point of view, this is the type of system that we have. This might be a home network, and this might be the corporate network. And on the home network it's unencrypted, on the corporate network again it's unencrypted, but over a public network, such as through an ISP, we have encrypted traffic. So we have tunneling mode or transport mode. Basic methods that we have is that we could have a remote access VPN where the remote user connects into the corporate VPN server and the communications is then secure. It should be noted that the encryption happens at the device and then is encrypted until it reaches the VPN server, and then it will typically be unencrypted after that. We can have an intranet VPN where we might have two corporate sites, and then they are connected through the public network through a VPN tunnel. And then we might have an extranet where we have two companies connecting over our VPN connection. It is important to understand the scope of where the encryption happens. In this case, the encryption is likely to happen between here and here, and not here and or there. The other key issue here is if the user is using other software, other connections, does all traffic go via the corporate site, or is it only the traffic which is destined for the local site? Okay, so this shows our issue here for this tunneling. Then we only have encrypted traffic between the two VPN servers, and it's unencrypted here, so that any firewall, any intrusion detection system can actually check the traffic. And end-to-end will encrypt the whole lot, so that these devices will not be able to check any of the content within the data packets. One method which is used, most companies prefer there not to be end-to-end traffic. So UDP port 500, as we'll see, is the port which is typically blocked on a corporate network, because this is the port that is used to exchange the encryption keys. Also, TCP port 50 and 51 are used in an IPSec data packets. So with the corporate network, these ports will be allowed. With inside, they will possibly be barred to stop any direct connection using a tunnel. IPSec uses an encrypted packet format called the Encapsulated Security Protocol, and it can also add on an authentication header to reduce the possibility of playback. This keeps the packet secret, and this stops playback. So basically what happens is that a data packet is taken, the header is kept, and the whole of the packet contents are then encrypted. An ESP header is added and a trailer, some authentication is added, and the data packet is resent. So you can see here that the original IP header is still here. This will provide both encryption and also this does not have authentication, so it could be involved in a replay attack. We can use it just for authentication, so that we don't have replay, and in this case it takes the IP packet, takes the header also, and then adds it back with a new header, and we can have an authenticated data packet. We can add the two of them together to get both encryption and authentication. Basically, the actual encrypted packets are actually defined in the protocol field, and in this case, protocol equal to 50 or 51 defines the IPsec. 115 is a layer 2 tunneling protocol. Basically, there are two main phases to setting up a IPsec VPN. The first phase is what's called Internet Key Exchange, and this is where the keys and the basic security policies are negotiated, after which they negotiate the actual details of the encryption. So in this phase, we typically define what Diffie-Hellman method we're going to use for the key exchange, what basic method we're going to use to authenticate each end. So on a PIX firewall, we can define a secret key and the destination that we're addressing to, and then we can define Diffie-Hellman the lifetime of the key. So it might be just one day that a key can exist, and then we regenerate the key. After which we go into phase 2, and with phase 2 we can actually define what traffic is it that we're interested in. because we don't necessarily want to encrypt all the traffic. So we might have key business data traffic. We identify that and we can encrypt that through the tunnel. All other traffic will be kept unencrypted. So we define what are called policies. With this, the two end hosts negotiate what type of encryption they support, what type of authentication they would like, what the interesting traffic is, and where the VPN is actually applied. So one method of authentication that we have is to pass public keys at the start between the two devices. And then we typically don't use public key for the actual encryption because it's too processor intensive. We basically use our public keys for authentication. Then we use something like the Diffie-Hellman method to negotiate a shared secret key, and then a shared secret key, and then we use that to encrypt the traffic. To keep authenticating, what happens is that we issue a challenge which has the result. We then encrypt that with our private key to give a hashed value. The hash value is then sent over, and the public key of the other side is then used to check this hashed value. There's an associated lecture which will go over the details of the configuration for the PIX ASA and also for firewalls, but this part of it, this lecture gives a quick overview of some of the configuration details. For PIX firewall, this is the phase 1, and then we have the phase 2, and we can see on the other side we have a similar configuration for the tunnel. This defines the other side, and here we have the same key which identifies it. It's not the strongest method of identifying it, but this is the key that they have. We can see that they identify their address as their form of authentication. Again, not the strongest, but it's certainly a valid method. We have pre-shared keys. Encryption is DES. SHA for the hash. Diffie-Hellman group 1. Lifetime of 86,000 seconds, and so on. The second part then defines which encryption and hashing methods it supports, what the interesting traffic is. So in this case, anything that's coming from 10.0.0, and we can ignore that part because of this, going to 192.168 should be encrypted through the tunnel. Again, on the other side, anything that's coming from 192.168 going to 10.10.0 from here to here should be sent to the tunnel, and then vice versa on the other side. So this defines the match, defines the peer that we're communicating with, and this defines the transform set. When they connect, they will negotiate in this phase as to which is the best and most preferred method of encryption that they'll actually use. PIX connecting to a router firewall is similar. Again, we define our basic policy, which should match up on the other side. We define the traffic of interest and apply it here. And we define our crypto map, which is the encryption and authentication methods that we're willing to use. So when we connect, we see this Internet Key Exchange port 500 appears here, and then we see this basic negotiation of the basic details that it can actually support. In this case, it supports AES encryption. A key factor is when a user connects to the VPN connection, what traffic actually goes to the VPN gateway and which traffic goes through the normal connection. So in this case, we can see on our client we can do route print. Route print will show us our interfaces. So in this case, we have a wireless connection and an Ethernet interface. And we can see here that the local address for this device is here. It uses a local gateway, which in this case is a wireless access point at this address. So all traffic goes to this gateway. So we haven't connected to the VPN connection yet. So you can see there that all the traffic will go to that gateway. Then what we'll do is we'll connect using our Cisco VPN client to a VPN site. We can see here that a VPN adapter is added. Now what we can see is that the default for traffic is still that same interface. But now we can see here that for the corporate network there is a new connection to find. So anything going to the corporate network will be sent to the gateway in the corporate network. Anything else will go in the normal route over the internet. Okay, so only traffic for the corporate network, which matches this part, will go to the gateway here. All other traffic will go out on the normal route. We can take an example of this. Before we connect to the VPN server, we can see here the route goes through the internet over various hosts. Once we connect, though, it will go straight to the actual, straight through the VPN to the actual connection. If we trace the route to another node with the VPN connection on, then we can see the route doesn't actually change. So the key to this is that the VPN connection needs to be set up carefully to make sure only corporate traffic goes through the corporate network. So tunneling is another key area that we have, and that makes sure that our protocols are tunneled and encrypted over a public network. One of the most popular is a secure socket. With this, we insert a layer between the application and our standard communication stack called the secure socket layer. And with this, we get certain key ports that we use. 443 is our secure HTTP. For email, we have 465 for SMTP, and so on. So what happens is that the user connects with an SSL connection, so this could be eBay here. So the connection is made, a certificate is passed from the server back to the client, and the client must accept the certificate for the tunnel to be set up. Normally, the user will be faced with the certificate first time they connect and accept its worthiness. Then it is cached so that whenever they connect again, then it is already there. Notice that it's only a one-way authentication, and it doesn't actually authenticate the user properly to the server. So this shows an example of FTP, which is a secure FTP. So you can see here it uses a different port 60, and it's using our SFTP. When we connect, we see the details of the authentication, the port, and the encryption that it uses, 3 DES in this case. So our FTP communications will now be encrypted and authenticated. A good example of this is that spamming is prevalent, and the basic protocol that's used to send email is SMTP. So because of so much spamming, typically ISPs block any relaying of email or any sending to port 25 on a destination domain. So the port will block port 25. So if a user wishes to send corporate email from home using the corporate SMTP server, they'll typically not be able to do it because the ISP blocks. The user themselves must then use the local ISP SMTP server to send the email. Port 25 is the typical one that we use. 143 is the receiving to read email. An improved method, and a method which is increasing, is to use an encryption tunnel to be able to contact a remote server. In this case, port 25 is still blocked, but we use a secure connection, in this case 465 for SMTP, a secure SMTP. So now we tunnel through, we connect to a destination on 465, and we can actually send through the network. As it's authenticated, then it is seen to be valid. We can do the same when reading email. In this case it's port 995 for POP3, and it's authenticated so that we can actually read remote email. You can see here Telnet, it's difficult to see. Telnet sends its data in clear text, whereas when we use our tunnel, we see things like the certificate and then the handshaking of this cipher details, and then our data should be encrypted. Okay, so that's given us a brief overview of some network security, some of the issues involved, looking at firewalls, both stateful and screening, NAT devices, an example of a PIX firewall, the usage of proxies, VPNs and tunneling. In an associated lecture, we'll go into more detail as to how these devices are actually configured.